Hello everyone and welcome to PrepFusion. This is the lecture 2 of control system subject, right? In the previous lecture, what did we study? Why do we need control system? Why? Because to check whether the system is we can implement the system or not, right? Whether the system is stable or not, whether the system is controllable or not, observable or not. Okay, all these things will be we can find from this control system chapter, right? And also we learned about Laplace transform, what is a Laplace transform, and few basic formulas for Laplace transform, right? A few fundamental signals. Okay, now in this lecture what we'll do few example problems on Laplace transform. Then we will understand the wavy curve method and also the concept of system. Like what do you mean by system, right? Control system I told you, like, control system, but what do you mean by system? So more in brief we will go into system, right? So first let us do few example problems. So we have this example problem, right? We have this example problem. Let's say this is the first problem. We have one signal like a pulse signal, right? So let's say this is going from going like this only, right? 0 until this point, right? And it is equals to 10 for this point. Okay, between 1 to 3 this is 10. Okay, this is our signal y of t. Now what like you need to find the Laplace transform. So pause the video and find the Laplace transform of this. Okay, so y of s, right? Find y of s. So how will you do that? Basically simple only, we have already solved this. So what is y of t? So what is y of t? Can we write this y of t in terms of unit step functions, right? So when is the step starting? It is starting at t equals to 1, right? And when it is ending t equals to 3. So positive sign will come at u of t minus 1. And what is the magnitude of the step? It is 10, right? So 10 into u of t minus 1. All this I have understand you. Or here from here you can understand. Put t equals to 1 here. T equals to 1. What do you get? Just t equals to 1 plus, right? What do you get? We get value 10, right? Value 10. That is what we are getting here. And put now what you need to do is until t equals to 3 minus, right? I mean 3 minus just before this, right? It should be 10. But just after this 3, right? It should be 0. So we have to subtract 10 from here. So subtracting 10, and when should this step start? It should start at t equals 3, right? So I hope you're understanding this. So this is the expression in time domain. So how do we convert this into Laplace? So this is simple only. Okay, I've already explained you the formulas, so I hope you're remembering, right? This is just a revision for you. So again, the Laplace for a unit step is 1 by s, but as it is shifted by 1, right, it will be e to the power minus s. So e to the power minus s divided by s, then minus e to the power minus 3s divided by s, right? So yeah, this is the solution for this question. Let us do another question, right? Let us do another question. Let me not name this. This is just h of s. Don't worry what is h of s and all, just h of s. And this time, right, we have been given the Laplace transform, right? We have been given the Laplace transform of a time domain signal. What we have to find is find the Laplace inverse. So I haven't explained you how to find the Laplace inverse, right? Like but you can do it. Okay, so what is the question? Question is find Laplace inverse of h of s. Okay, so how do we do it like we can do the partial fraction formula, right? What you can do, like you can do it in one instant also, but I'm explaining you how to do it. So what you can do is, like, we know that this 1 upon s plus 2, 1 upon s plus 3, if they are separated, right, we can easily solve this here. What is the 1 upon s plus 3 and 1 upon s plus 2? That one was like if some exponential is multiplied, right? If some exponential is multiplied in the time domain, then we can easily solve this. And the other part, this 1 upon s, is just a step part, right? So what I need to do is break this down into two components, right? So what I will do partial fraction basically. Let me write solution here. a by s plus 2 plus b by s plus 3, right? So yeah, now what is this a and b? What are these coefficients? What is the value of a? We can find simply like this. A will be equals to h of s at s equals to minus 2, right? S equals to minus 2. So how are we doing that? Like that also I will explain you. Let me like further write this equation. How is this coming, right? So okay, this got shifted. So what I can write instead of h of s, right? What I can write instead of h of s? So I can write this h of s, right, as 1 upon s plus 2 into 1 upon s plus 3. Now what you do, multiply by s plus 2 into s plus 3 on both sides, right? So this becomes 1 on this side, this becomes s plus 3 plus b into s plus 2. Okay, so now like if we put s equals to minus 2, we get that we are only left with a, right? So here from this equation you also can solve. Okay, this equation you also can solve. There are multiple methods. You have already solved all this. So when we study Laplace, right, we learn all these methods. So putting like s equals to minus 2, what you get, this becomes 3 minus 2 1, so a becomes 1, a becomes 1 only, and b equals to simply we put s equals to minus 3, right? S equals to minus 3, so h of s equals to minus 3, which we get as, here we put minus 3, right? So this is 3 minus 3 plus 2 minus 1, so b equals to minus 1 only, minus 1. Okay, b equals to minus 1 only. So what would we write this now impulse function as? H of s equals to 1 by s plus 2 minus 1 by s plus 3, right? 1 by s plus 3. Okay, so from here we can easily find the inverse Laplace. Like this is just 1 by s plus 2, right? And what is 1 by s plus 2? What we are understanding, s has been shifted by 2, so some negative exponential should have been multiplied at the time domain, right? And here s has been shifted by 3, so some negative exponential will be multiplied by the step function, right? By the step function, because we are just 1 over s. Okay, so I have already explained all of this. So it should be e to the power minus 2t u of t minus e raised to the power minus 3t u of t. Okay, so I hope you're revising all those formulas, right? All those will come handy. Okay, and also like by default, like this is u of t only, because you may get confusion like why are we writing only causal signals? What are causal signals? I explain. But in control system, right, in control system, whole of the control system will only work with causal systems. What is causal, I will explain you, but just write this down. In control system, we will work only with causal systems. Okay, in control systems we will only work with causal systems. So this is very important part. What is causal? I'll explain you, don't worry. Now let's go to another example. We have been given one time domain signal, right? We have been given one time domain signal h of s, right? It is like not h of s, sorry, time domain signal. So this should be x of t equals to, so minus t u of t, right? Is minus t u of t. So what we need to find is the time domain, a Laplace domain expression for this, right? Find x of s. Now this is like one thing what we are familiar with. We're familiar with this part, right? This part. What we see is this is just a ramp signal, right? And what is the Laplace of a ramp signal? It is 1 by s square. Now we're just multiplying a ramp with one exponential term, so that s, right, in the Laplace domain will be shifted, right? So what will happen? First what you can do is, this is the like method 1 for solving this question. What you can do is like find the Laplace of the ramp signal is equal to 1 by s square, right? 1 by s square. And what you need to do is like now just we are multiplying with exponentials, so the s will be shifted by 1, positive 1, right? So Laplace of e raised to power minus t u of t, it will be 1 by s plus 1 whole square, right? So this will be the answer for this question. Now how to do this using another method, right? Using another method. So one thing you remember, right? I have like taught you the concept of multiplication by t in time domain, right? In time domain. So all these are revision, right? So here, yeah, this is the integration and this is the differentiation, right? If you multiply t with some x of t, right, then we differentiate in the Laplace domain with a negative sign, okay, for just a single multiplication for like t to the power n, then this formula comes up. So all these are revision, right? So yeah, so now what will be the method 2? Okay, I don't have enough space. Yeah, so method 2, right? Multiplication by t in time domain. Okay, so please ignore the outside noise if it is coming. Okay. Multiplication by t in time domain. Okay, so like what will happen? First I will find the Laplace transform of this signal, right? This signal, this is easy. This is just exponential signal, right? Exponential signal. So what is the Laplace transform of this? It is basically, let me write this down, different color. Laplace transform of e raised to power minus t u of t, just an exponential signal, right? If it's just exponential signal, what is the Laplace transform? It is basically 1 by s plus 1. Okay, now what you do is multiply by t on the time domain, right? So what will happen? Differentiate in the Laplace domain, frequency domain. T into x of t should be minus of dd of s into x of s. Okay, so the Laplace transform of t into e raised to power minus t u of t equals to s plus 1. Okay, so what is the differentiation of this? Simple only, right? Let me take another page. Laplace transform of, okay, let me not write this, actually I'll write this later. This is minus of 1 over s plus 1 whole square, right? And we get this as 1 over s plus 1 whole square. Okay, so yeah, this is the answer for this question. This is answer for this question, right? So this is basically the Laplace transform. Now like let's do the Laplace transform. These were the few example problems. You do more problems, you just search in Laplace transform problems, or I will provide you more problems. Okay, now let's do the Laplace transform of passive elements, right? How are passive elements represented in Laplace domain? So I hope like Himanshu has already taught you this. Okay, Himanshu, I know Himanshu has already taught you this. I just go in brief, right? So for a register, right? For a register, what is the current and voltage defined in time domain, right? How are the current and voltage related, right? So this is just a resistor. Okay, this is the voltage v of t and this is the current I of t. So how are they represented, right? So v of t is equal to I of t times r. Okay, I of t times r. Now what we can do is, here there is no differentiation or anything, so Laplace transform of this v of s signal will be v of s only, I of s signal will be I of s only, and since this is multiplied by a constant, right? There isn't any time domain expression or anything, this is just multiplied by a constant. Okay, so we can simply write this outside, and this equation will be converted like this. So we can convert this like this: v of s, I of s times r, because this is a constant, r is a constant, right? R is a constant. Okay, now what we can write is, what is the ratio of v of s by I of s? That is the impedance, right? So impedance in the Laplace domain, how we can write? So is equal to this is equal to r, this is equal to r, right? So yeah, this is just the impedance in Laplace domain for a resistor, right? Now what will happen for a like, let us do for an inductor first. Okay, let us do for an inductor first. So what will happen for an inductor? So the inductor is like this only. This is the VL of t, and this is the IL of t. Okay, so how are the voltage and currents defined? So is equal to L dIL of t by dt, dIL of t by dt. Okay, so now can you take the Laplace transform? Now what we know, Laplace transform of VL of t will be only like VL of S only. Laplace transform of differentiation of a signal, right? What will be happen? We'll just multiply by S. How? Just I've explained you that this in the previous lecture, right? Let me find that here, right? I think I forgot to write here. Yeah, I forgot to write here that here, right? I was explaining you this, like when we differentiate, right? Step differentiation of step is what? Impulse, right? And differentiation of ramp is what? Step, right? How? Ramp is a constant, right? Slope, ramp is increasing linearly, right? And slope is constant, slope of which is constant. So if we differentiate, we're just writing the function as slope only. So slope is constant only. So how does it look? It looks like a unit step function, right? It looks like a step function. That's why we differentiate the ramp, we get unit step. Now step, right? Step, what is the slope of the step? Slope of step is always zero, but it isn't zero at one point when it is not zero. At t equals to 0, right? T equals 0 is suddenly increasing, right? After that it is constant. So differentiation of any constant signal, right? Slope of it is 0 only, it is not changing. So yeah, impulse function is like that only. It's 0 everywhere, but it's suddenly increasing at t equals 0. So that's why differentiation of this is this. Okay, but also we did the Laplace transform of this, and what we found out was, if we multiply S with this, right, we get impulse. If you multiply the impulse, if you multiply the Laplace transform of ramp with S, what you get? Unit step. So what are we understanding? That if you do differentiation in time domain, we have to multiply by S in the frequency domain. So yeah, I think I missed the point in the previous lecture, so I try to again explain it to you in a better manner. Okay, so yeah, that is what we'll do here. Okay, also like in this also I forgot. No, in this is, that's fine, this question, that's fine. Okay, so this is differentiation, right? So what will happen? It will simply be VL of S only, because Laplace transform of, like, let's say, what is Laplace transform of x of t? It is x of s, right? So we don't know, but yeah, this is VL of S, right? Then L is a constant, and dIL of dt will be what? Will be simply IL of S times S, because S will be multiplied. Okay, let me, S will be multiplied. Okay, so what will be VL of S by IL of S? So equals to SL. This is the impedance. This is the impedance. This is the impedance for a inductive circuit, right? So this is all this he have already explained you, right? Now what is for a capacitor, right? For a capacitor, this time I will not explain further, because this is for the integration part. Or this also you can do the differentiation part also, but from integration also you can do. So what is the, like, this is the capacitor, right? Let me do this a bit quickly. This is VC of t, and this is IC of t. Okay, so what is IC equals to? IC of t, right? It is equals to C dVc of dt. We can integrate both of this side, or we can just derive from here only. So Laplace, let me write the Laplace here. We're taking the Laplace transform, else you will not be able to understand. So Laplace transform, right, is I of S C V, this is IC, VC of S times S, right? We have to multiply S also. So now what is the impedance of this capacitive circuit, right? So ZC of S, sorry for the burping. Okay, ZC of S equals to VC of S by IC of S equals to 1 by C of S. Okay, so this is the impedance for capacitive circuit. Now let me summarize all these things, right? Let me summarize. So element is R only. Let me write this in different color. RLC. So for R, right, time domain extension is V into I into R. This is VL equals to L DIL by dt and ic equals to c dvc by dt, right? So what we can do simply, what is the Laplace transform of r? Then it is simply r only, because from what we can understand practically, that resistance does not depend on frequency, right? It does not depend on frequency, it remains constant. But there is something dependence on resistance on frequency, but that is another thing that we know as the concept of AC resistance. That is different. But in general, right, resistance doesn't depend on frequency only, doesn't depend on frequency at all. So the Laplace, the frequency domain should be same as the time domain. That's why we get something like this. But the inductance and the capacitance, they depend on frequency, right? They depend on frequency. So that's why they are changing, right? They are function of s, they are function of frequency, their impedance, right? So this is L, this will be SL only, and Laplace transform C will be 1 by Cs. So if we see one circuit element as L or R, C, what we'll do, we'll convert this into SL, or C, we'll convert this into 1 by Cs. We will do examples from there. You will understand. In the next lecture we'll do examples, right? Now what we'll do is study a bit of a mathematical tool known as wavy curve method. So what is a wavy curve method? So basically this method is used to find whether signal is positive and whether signal is negative. Okay, so this may come in handy in few chapters. So yeah, we'll just learn this pretty quickly. So let me take an example. Okay, f of x equals to x minus 1, x minus 3, x minus 2, right? F of x minus 1, x minus 3, x minus 2. Okay, so what we need to do is, like, can you tell me just by seeing this function, where is it positive, where is it negative, and all those things? Just write me the range. You just can't suddenly do, instantly do. You have to think about it, right? So for that we have a method, right? What we can do is, we find the corner points. What are the corner points? Corner points are the points where this function, like this bracket terms, right, are getting 0. Okay, so what is the step 1? Find corner points. Find corner points. Okay, find corner points. So yeah, this is the corner points. Now what we'll do is, we'll check at the maximum corner point, is the function positive or negative. Okay, so what are the corner points for this? One, 2 and 3, right? So at x equals to 3, we'll check whether this like x more than 3, whether this function is positive or negative. So obviously this will mostly be positive only. Okay, at maximum chance it will be positive, because everything becomes positive after that. Everything becomes positive because this is the maximum value. So it will always be positive, but just have to keep in mind, okay, whether this is. So at x greater than 3, f of x greater than 0. Now what we'll do, we'll draw the number line, right? We'll draw the x-axis, just the x-axis, just the x-axis. Okay, now we'll mark the corner points here. So what are the corner points? One is 1, another is 2, another is 3. Okay, just don't think that this is not symmetrical or something. Okay, there's symmetrical, there's symmetrical. Okay, so now what will happen? Now like at x more than 3, right, this is positive, this is more positive, right? So this will be positive. I will write this as positive. What you can do is, you can like let me first draw it, then I will understand. Now what will happen between the corner points, right? Between the corner points the sign will change. Like after every corner point the sign will change, and when it will not change I will explain you in the next example. So before, like after 3 it is positive, before 3 it will be negative, it will become negative. So it will become negative. Okay, it will become negative. Now before 2, right, what will happen? It will become positive only, because after every corner point it changes, right? Again before 1 it will become negative only, it will become negative only. Okay, so this is like how we draw this. Now from here instantly you can say, just hold on a second, sorry, actually a call came up, so like I have to take the call. Where were we? We were actually explaining that we have the corner points. We know now from seeing this, like seeing this plot, right, we can exactly say between which range x is positive and x is negative. Like many people plot this like differently. Also, like what you can do is you can plot like this wavy, like the name says, right? Wavy curve method. You can plot like this wave also. It doesn't matter. For me, visualization, it's easier to draw and it's more fast. That's why I draw like this only. You can draw like this wavy curve also. Like this explains that this part is positive and this part is negative. That is more visually like appealing to you. If it is more visually appealing to you, you can draw like that. Okay, but it doesn't really matter. Okay. Here, what we'll do, we'll write the range for which f of x is positive and write the range for which f of x is negative. So, for the range which f of x is positive, right? So, x should belong to, when it is positive, it is like between 1 and 2, right? 1 and 2 it is positive. Between 3 and infinity it is positive. 1 and 2 it is positive, and union, I hope you all know this class 10 things. Okay, class 11 things, I don't know, remember exactly. So 3 and infinity is positive. Now what should this brackets be? Should this be open or close? So for that, right, we have to check at these corner points. At x equals to 1, we're getting 0. So this like this should be closed only, because 1 isn't included. Is in this range, because we only want the positive values of f of x, right? We only want the positive values of f of x. So 1 isn't included, so 1 will not be included. 2, similarly 2 will not be included anyways, because the function is not defined at x equals 2, because we get it 0 at denominator. So function isn't defined anyways. And x equals to like 3, again function is getting 0, but we only want the positive values, so it will define only at positive. Okay, so yeah, this is for this range. Now let's do it for f of x less than 0, right? Let me just keep it bit over. So for this range, right, x belongs to minus infinity to 1, then union 2 to 3, right? Union 2 to 3. Okay, so yeah, this is what f of x is. Now like let us do another example. From that you will understand in a more better manner. The first one more thing is that the question may be twisted, right? The question may be twisted. In what sense? I will just give you another question. Let's do this example, right? Let's do the example, right? F of x equals to this simple x into 1 minus x minus 2 x minus 3. Okay. X minus 3. Okay, so yeah, this is the f of x. Now like is this our normal format? Our normal format was this coefficient of x, right? This coefficient of x should always be positive, right? So what we'll do, we'll convert this into our normal format. But first, like, what is the question? If I were to ask you the question, find the range for which f of x is find is positive, right? F of x is positive. First, what we'll do is convert this f of x, right, into our known format. So this is x minus, let's wait for the bike. Okay, this is x minus 1 divided by x minus 2 x minus 3, right? So this is what we get as our format. Okay, I think yeah, that is fine. This is what we get as our format. Now what we'll do is simply, I think I had a change in this question, because I think this was x plus 2. Okay, just make a slight change. This was x plus 2, so this will also be x plus 2. Now we converted this signal, right? Now what we'll do is find the plot for this function, then just oppose the sign, right? Like make the signs opposite in the plot, then we'll get our, because then you get our actual plot, right, of f of x, because we're just multiplying by a minus sign, right? So it will just make the sign opposite of whatever it was. If it is positive, it will become negative. If it is negative, it will become positive. So let me write another function, f dash of, or like yeah, f1 of t, because f dash of x is means something different, right? So let me write f1 of t. We'll just plot for without the negative sign. So what will be the plot for this? I'll just do really quickly. What are the corner points? Corner points are -2. 0 is also corner point, right? Because at x equals to 0, this is becoming 0, right? So 0 is also corner point. 1 and 3, right? -2, 1 and 3. Okay, now let me draw the number line. So this is the number line. Okay, let me write the corner points here: -2, 0, 1 and 3. Okay, now what will happen? Now obviously x more than 3, right? This will always be positive, always be positive. Okay, so what we'll do is x more than 3, this is positive, then it is 0, like negative again between 0 and 1 it is positive, and again this is negative, and again this is positive only. Okay, so this is how this will work. Now what I'll do, I just flip the signs, right? I will just flip the sign. This is for f of x1. What I will do, for f of x, just flip the signs, right? Flip the signs. Okay, so what will happen? If you just let me mark the corner points, right? This is -2, 0, 1 and 3, right? So yeah, this will become negative. So this is negative only. Between 1 and 3 we will get positive. Between 0 and 1 we will get negative. Again between -2 and we will get 0. Okay, so this is what we'll get. This is what we'll get, right? So yeah, this is negative only. So for what range this is positive, we have to find for what range x is positive, or like f of x is positive, right? So we can simply do is that, like f of x is positive for x belongs to this -2 to 0 union this 1 to 3. Okay, so I can also ask for what range f of x is not negative. What do you mean by not negative? So for what range f of x is not negative, right? So it is not negative. That what does that mean? So that means f of x should be greater than or equals to 0. This time equals to sign also comes. So this will be slightly changed, right? So positive range will remain only, but there is one extra thing that we need to check for is the like equals to 0. When is the function 0 also? So at this corner points, right, we have to check corner points. We have to check whether the function is 0 or not. So we will only check for the numerators, because denominator the function is not defined. So the numerator corner points, right, this is 0 and this is 1, right? This is 0 and 1. So at x equals to 0, yeah, this function is going to 0. At x equals to 1, this function is going to 0. So this 0 and 1 will be included also this time. So how will, do we include? We just put square brackets, right? We just put square brackets. 0 and 1, 0 and 1. We just put square brackets, right? So yeah, this is basically what a function is. Just one more example, like when does the sign doesn't change. Okay, sign doesn't change. This is the last example. After that we'll finish this lecture, right? So what I will do is take another example. Let me like put this in quotients only. So this is like, that was the third quotient. This is the, let's say this is the fourth quotient. This is the fifth quotient, right? So we have been given one function f of x. This time, right, we have like square terms also. Okay, cube terms also. So this is x minus 1 whole square, x minus 2, then x plus 2 whole cube times x times what was this, x plus 3, I think. No, this was, sorry, x plus 1. Okay, so yeah, this is the function basically. Now everything is same, right? Everything is same. We have to find the range for which f of x is greater than 0. Okay, f of x is greater than 0. What we need to do is basically the procedures will be same. Just if there is some even power with the corner point, right? Even power with the corner point, this is even, right? Hence the sign will not change. Sign will not change. If there is odd power, then the sign will change. Anyways, every time previous examples, right, there were odd power. 1 is an odd number, right? So there was odd power with the corner points, so sign was changing. But here we have even power, right? Sign will not change from transition from the corner points. How I'll explain. First, let me write the corner points. Corner points are this, let me find the, yeah, -2, -1, 0, 1 and 2. These are the corner points, right? So now what I will do, I will just draw the number line, right? Draw the number line. -2, -1, 0, 1, 2, right? 0, 1, 2. So this is like more than 2, we know this is only positive only, because everything is positive. More than 2, right? It is the maximum corner point, so this is positive only. But at 2 we have, like, at 2 we have odd power only. We have odd power only, odd power. So sign will change. Sign will change, right? Now at 1 has even power. 1 has even power. So sign won't change. It will still remain negative. Still remain negative. At 0 we have only odd power, so sign will change this time. Okay, sign will change this time. At -1 we have odd power, so sign will again change. Okay, okay, let me draw this with different color actually. And at like before -1, right? Before -1, like, what is this is like this is like a odd power only, so again sign will change only here. And at -2, right, again at -2 we have odd power, so sign will again change. So only this point was the interesting point, this point, right, where the sign didn't change. Why? Because at 1 we had even power. So for what range this x is positive, right? So x is positive between this -infinity to, we're doing open brackets because I'm not including 0 here, so -infinity to union -1 to 0 union 2 to infinity, 2 to infinity. So yeah, this is what our range look like. So now let us go for like another concept of systems. What is basically system? But before that, right, before that, just one more thing I need to tell you about the Wavy curve is that, like, if the function is complex, has complex roots. By complex, let's say if f of x, right, is x squared plus x plus 1, this has complex. How do you understand complex? Just find the discriminant and it will be negative, right? It will be negative. So this discriminant for this, b square minus 4 is 1 minus 4, so it is -3, and it is negative, so it is complex. So you just have to check for one value. You just have to check for one value, and if it is positive, then it will always be positive, and if it is negative, it will always be negative. Why? Because it doesn't cut the x-axis, right? If it is positive, it will be something like this, and if it is negative, it is something like this. It never cuts the x-axis, so it doesn't change its sign. Okay, it doesn't change its sign. So you can just simply write like this also. So this one thing I have to mention to you. Okay, so now we will start systems, right? So basically what is a system, right? So a system is basically, it is a group of physical components which give proper output for a given input. So you can think like, as I explained in earlier examples also, you can think as anything as system, right? As a fan, as AC. So what do? We give some input, right? We turn on the switch, then the fan gives us output as like air or something, okay? So it gives us proper output, okay? So now we have to control it also. We control it through regulator and all those things. We have to control it also. All those things will come, okay? So like that, you can understand the system. We give some input to the system and we get some output, desired output, right? So how do we represent the system in in control system, right? So in control system, we represent it in terms of block, okay? So let me draw this. We're giving some input, right? And this is the system, and we are getting some output, okay? So now in more broader terms, how we can say, let's say system is an integrator, right? It is an integrator. Like in analog circuits, you have studied that we have an integrator circuit. So if we give x of t input, then we'll get output as integration of x of t, right? Y of t. So that can also be explained as a system also. So let's say system is an integrator, right? So what will happen if we give the input as x of t, we'll get the output as integration of y of t, sorry, integration of x of t. Okay, let me not write this like this. Okay, so this is the like this is basically what a system is. So basically, what does a system mean? We give it some excitation and we get some response, right? But in our case, right, in our control system, we'll always study LTI systems. By LTI, I will explain you what does that mean, okay? So again, let me take this, right? So we give it some excitation, like in control system terms, we say it as excitation or input, right? So okay, let me not delete this, excitation or input. So all these are just terms, not that important, okay? Excitation, and we measure the output or the response, like how is the system performing with a particular excitation. Now for LTI system, I will explain you in the data set. Let me first write this. This is response. This is response. Now for a LTI system, right? For a LTI system, if the input is x of t, like this, you have to study in signal system, then the output, just remember this, okay? Just use it to remember this. Output will be h of t convolution with x of t. Now you may ask, what is h of t? H of t, right? H of t is the impulse response of the system. H of t is the impulse response of the system, okay? What do you mean by impulse response? I will explain, but just understand this thing, that like if you give some like in control system, if you give some input x of t, then our output, right, for a LTI system, linear time invariant system, the output will be the impulse response convolution with the input, okay? Now what is an impulse response? Impulse response is the output that we get from the system when we give an impulse signal as input. When this x of t, right, when this x of t is impulse signal itself, the output that we get is the impulse response of the system, okay? Why are we so much interested in this? I will just explain in next few slides. So this is the output that we get from the system when we give impulse input to the impulse input to the system. Okay, so yeah, this is one important thing. Now, like our system, right, in control system we will only study LTI systems. Why, I will explain. But what is LTI systems? So LTI systems, all the transfer function, like transfer function will be defined for LTI systems only. So that's why it is important to, like, we are only involved with LTI systems. And like what is a transfer function, I will explain in next few slides. Like in control system, just keep watching and writing, everything will be you will understand everything just part by part. Okay, if you keep watching. In control system we are only concerned with LTI systems. Okay, LTI system. Now this impulse response, right? So what is the special property of impulse response? Basically, if you know the impulse response of a LTI system, right, LTI system, then we can find the output for any type of excitation, whether it be unit step, whether it be ramp, any type, sinusoid, anything, if you know the impulse response of a LTI system. But if we know the impulse response of a non-LTI system, we can't simply give the output, we can simply write the expression for the output for any type of input, right? We can't. Okay, so that is the difference between LTI and non-LTI system. And don't worry, in control system we are only concerned with LTI system, so you don't even have to worry about that. Okay, about non-LTI system. But one thing you need to know, you should know, is the impulse response is valid for all systems. What does impulse response mean? Basically, when you give impulse response, basically when you give impulse input, what is the output that we get? That is what the basic meaning of impulse response is. But the importance of impulse response increases when we are concerned with LTI system, because if we know the impulse response of a LTI system, then we can simply find the output for any type of inputs, right? Any type of inputs. That is why the importance of impulse response is very high in case of LTI systems. For non-LTI, it isn't that high. So I should write here is impulse response is valid for all types of systems. Okay, all types of systems. So now, like what we'll understand is like I've already explained you, like we are only concerned with LTI system. Now what is LTI system? So LTI means, I've already explained you what is a linear function is, right? It follows the principle of homogeneity and superposition. Now I'll explain what is TI. Like LTI means linear time invariant. Okay, LTI means linear time invariant. Okay, so yeah, now you have to understand what is time invariant. Also, one more thing, that in control system, right, we're only concerned with causal signals. I told you I will explain you what is causal. So first, like, let us understand what is a causal signal is, right? So that, what is the difference between causal and non-causal? So for causal, right, for causal, the present output of the system, right, the present output of the system that we receive should only depend on the present or the present plus past input. So I should write this input here also, present input or the present or past input. By this, what do I mean? So let's say we have one signal, right? Let's say we have one signal, y of t equals to simply x of t minus 4, right? T minus 4. Now I want to get the output of the signal at t equals to 0. T equals to 0. This is the output, and this is the input, right? This is the relation between input and output. So at y of 0, what is the from where, which instant we are taking the input from? So it is x of minus 4. So this is past, right? Minus 4 is past, 4 seconds before. So yeah, this should be a causal system. Okay, because the output is dependent on the previous input. Okay, or I want to know why the instant y equals to 1, what is the output at y equals to 1, t equals to 1? What is this? Well, this x of minus 3, right? So if this is x of minus 3, so again we are taking it from past, right? So this will be causal. So for a causal system, the output should depend on the present input or the present plus past input. So this is very important. Now from this, right, we'll understand the difference between causal and non-causal, and we'll actually understand the meaning of causal. So for non-causal, right, the present output should be depend on the present plus future, past plus future, or present past plus future. So future term will come, right? So there should be some dependency with the future, then then the system will be non-causal. But in actuality, in reality, like still we can't realize a non-causal system, because how can we predict the future, right? How can we predict the future? But like this is the signal thing, so future is important here. Oh shit, future is important. Okay, future is important. So let me write down a few examples. Let's say we have one signal y of t, like output dependent on the input as x of t square, right? X of t square. So now if I want to find y of 0, we are getting x of 0. Now this is fine, okay. Input and output are dependent on the present time only. But if I want to find y of 2, right? Y of 2, what is the input this time? It is x of 4. So for t equals 2, for the instant t equals 2, if I want to get an output, I have to get the input at x equals to 4, right? Future, right? Future. So how will I do that? That is basically non-causal system. Non-causal, it doesn't depend on the present, it is depending on the future. Present plus future, or whatever you want to do. Present plus future. Okay, so yeah, this is basically the difference between causal and non-causal. Like this is one thing. Now I will like teach you that what is time invariant, right? What is time invariant? So what does time invariancy mean? So how is this system time invariant? So here, if the input is shifted by t naught, then the output should also be shifted by same amount. Okay, let me just write this. You will not understand this. We'll just do a few examples, then you will understand. If input is shifted by t naught, then output should also be shifted by the same amount, that is t naught only. Okay, so let's say for this example, let's say I have one parabolic signal, right? Parabolic, like x, y is dependent as x, y and x are dependent like this only. Okay, so y equals to y of t equals to x square of t. Okay, so what I will do, I will just shift this x of t by t naught, then this output should also be shift like this only. So how do we prove time invariancy, right? How do we prove time invariancy? So let me, this is example. So what I will do is simply find the response, we say it as response of this input signal, right? I will just shift it by t naught, right? So what I will do, I'll just simply shift this whole bracket term by t naught. Okay, in time variant we will understand this concept more rigorously, like what exactly are we doing. So if I find the response of x square of t minus t naught, so this response, right, what we will get is basically it will be x square of t minus t naught only. We're just shifting this signal by t naught. Okay, by shift I will explain you. This is response. Now if I shift this output by t naught, what do we get? So if I make y of t minus t naught, we get x square of, like we're just changing the t as t minus t naught, so the relation x square will be t minus t naught only. So what we can see, the response and output. So system is time invariant. So here we're just shifting the response, right? Shifting the x of t, where we're like using this signal, shifting the x of t this time, and inside this bracket term only. This bracket term we are concerned with only, okay? We are only concerned with this bracket term. Just remember, when we are finding the response, right, we're just shifting the signal x of t by t naught. But when we are shifting the output, right, we are shifting this whole term, right, this whole y. We're changing the t. We're changing the t this time. We're changing the t from t to t minus t naught while doing this, while changing the output. But response, right, we're just using this bracket term and we're shifting it by t naught. We're just subtracting by t naught. We just subtract this bracket term by t naught, whatever is in the bracket. If in this bracket it was t square per se, we'll do the t square in the next example. If it was t square, if we want to find that response, right, what we'll do, we'll do t square minus t naught only. But in the second case, right, if we want to replace it by t minus t naught, what we'll do, this will be t minus t naught whole square. This will be t minus t naught whole square. Okay, so yeah, this will be that only. This will be that only. Okay, so yeah, in the next example I will explain you, like in the time variant example, right? So here time variant, right, if input is shifted by t naught, then output will not be shifted by same amount. Okay, output will not be shifted by same amount. Okay, let me just check how much do you record. Okay, which is almost 1 hour. Okay, output will not be shifted by same amount. Let me take an example. So let's y of t equals to x of t square this time, x of t square. Now whenever there is a function of time inside the bracket term, right, most probably, most cases, okay, most cases, if it is not linear, okay, it will be time variant. And if some function of time is multiplied with this x of t, right, with this x of t, then also it won't be linear. Okay, I'll do another example. So now let me find the response of this x of t minus t naught, right? So what will happen if you want to find the response of x of t minus t naught? What I will do, simply shift this whole signal by t naught, right? Now what I need to do is find the output. If it is shifted by t naught, it should be shifted by same amount for time invariancy, right? If it is not, if it does not follow the time invariancy, then the system will be variant only. Okay, that's why we will check for time invariancy. If it does not follow, then the system will be time variant, right? So we're just replacing t by t minus t naught. So this is x of t minus t naught whole square. Okay, so this will be x of this will be different, right? This will be something different. So these are not equal. These are not equal. Okay, these are not equal. Okay, all these things you will study in signals anyways. Okay, I'm just giving you a brief idea. So system will be time variant. You can check it for yourself. Some function of time is multiplied with this x term, then also the system will be time variant, because the response won't be same anymore. Okay, because what we'll do, we'll just simply change this bracket term, but while calculating this term will also change. Okay, so then also response won't be same anymore. So like I've already explained you why are we interested in LTI system, because like if you know the impulse response, then we can find the output for any type of input, right? Any type of input. Okay, just by convolution of just finding the transfer function. That's just by finding the transfer function. What is the transfer function? I will explain. Okay, so like for LTI system, the impulse response will be LTI signal, right? LTI signal. So these things you have to keep in mind. So I think that's it for this lecture. So all these things I have explained you. Write note those points which I tell you. Okay, so that like why are we interested in impulse response? Why is the importance of impulse response very high in LTI systems, and non-LTI systems it is not that high? Why I have already explained you. I'm still explaining you that for LTI systems, right? For LTI systems, if you know the impulse response, then we can easily find the output for any type of input. Okay, But for non-LTI systems, we won't be able to find the output because we don't know the transfer function. Don't know the transfer function. Okay, what is the transfer function? I will explain in the next few slides. Okay, next lecture, that is basically. So yeah, like what did we study? Let me just quickly revise. What did we study today? We did few example problems, right? We did few example problems like this, all these things. I hope you are revising the formulas, like how to do partial fraction, then basically how to like do this. We have two methods for doing this, right? Let me draw the pen again. We have two methods for doing this. Okay, first method is simply that formula that we use for t, right? T is 1 by square. Now multiply by exponential, it becomes s is shifted by 1. Okay, and in this case, right, in this case, use another property, multiplication by t property, then we differentiate it. So yeah, that you can use. Then we found the Laplace transform of different components, passive components. I hope like Himanshu has already taught you. Just in a brief, we went through. This is a summary. This is the main thing that we need to remember. Whenever you see r, you replace with r. Whenever you see L, you replace with SL. Whenever you see C, you replace with 1 by CS. So example problems we'll do in the next lecture, right? So yeah, again we study the wavy cup. This you study in the 11th 12th. So this I just give you a brief overview and revision of what is a wavy cup, and this may be required in next lectures. And then I told you what is a system. System is if you give some input, we get some output, right? If you get some excitation, we get some response. Fan, AC, washing machine, fridge, TV, everything is system. Everything is system. Okay, so you are surrounded by systems. Okay, so I told you the concept system, then I told you the impulse response concept. For LDA systems, the output will be will be related to the input like this: convolution of impulse response with x of t, right? With x of t. So that's why the importance of impulse response is very high for LDA systems. Okay, but impulse response in general, it is defined as the response to a system when we give some impulse input, right? So that is the what the basic meaning of impulse response is. Okay, so yeah, all these things we studied what is LTI, what is causal, non-causal. Causal is what? Causal system, the output, present output should depend only on the present input with or present plus past input. It should not depend on the future. That is the most important. The output should not depend on the future input, right? Output should not depend on the future input, then it will be causal signal. If it is a non-causal, right, if the output depends on future signal, then it is a non-causal signal. Okay, this is the main thing that you need to keep in mind. Time invariant, I've already explained you that if we shift the input by t naught, the output should be shifted by same amount, then the signal will be time invariant. Already explained here, right? And like from time variant, your idea getting more clear that what does input shifting mean and what does output shifting mean. So if we shift the input, right, we're shifting just this bracket term by t naught. Okay, that is more, which is shifting the input by t naught. And if you're shifting the output is like replaced, t is replaced by t minus t naught. So here it will also, this whole bracket, this t will be replaced by t naught. This bracket term won't be replaced by t naught, right? This t will be replaced by t minus t naught. Okay, and if these two, response and the output of the system, both of them shifted by t naught, are not same, then the system will be time variant. Okay, yeah, that was it for this lecture. In this lecture we'll cover what is transfer function and few example problems and a lot more things. Thank you for watching.